Hello everyone and welcome back to this online course on aquatic geochemistry. We were discussing redox reactions in our previous lecture and we are going to discuss more in this particular lecture. Now we learned how to write redox reactions, we learned how to write PE of the reaction, we learned what is EH of a reaction. Now, from EH we are now going to learn what is the Nernst equation. Okay. So, the electropotential EH that we are going to measure, how do we write it? Okay. So, it is calculated. So, for example, if there is a reaction where A plus B accepting electrons and forming C plus D, okay, how do we write in terms of a EH equation? In terms of EH, it will equate to E0 plus RT divided by NF into ln of the the reactant divided by the product. Here if this is positive, then you have this kind of denotation. If you just switch it in the other side, that is a Q, that is where product divided by reactant, then it becomes the negative sign. Okay. So, this symbol, just keep a note that if you are using product by reacting, then it should be negative. If it is reactant by product, okay, if it is reactant by product, then only it is going to be positive. Okay. So, again RT, R is my gas constant, T is my temperature, N is my number of electrons that is exchanged and F is the constant. Okay. And what is E0? E0 we know from this term, delta G0 R is equal to NFE. Okay. So, this is E0 coming from this term. Okay. E0 term is coming from my free energy of the reaction. So, let us consider an example, let us look into an example. So, NO3 minus plus 10 H plus with 8 electrons getting exchanged accepted forms NH4 plus and water. Okay. So, it is nitrate forming ammonium ion. Okay. If you are going to write the EH of the reaction, what will it be? It will look like EH, which is equal to E0, E0 is coming from this, minus 0.0592 divided by 8, okay, 8 is the number of electrons, okay, into log to the power. Here since it is a minus term, so here it will be product divided by reactant, right. So, the product term is activity of NH4 plus. This term will not be there because it is a pure phase liquid. So, in the denominator we are going to have NO3 and H plus. Thing to note is we are not going to add here any e to the power minus. In terms, when we are writing in terms of EH, activity of the electron is not written. Okay. So, we are not going to write this term anymore because this is what we are going to measure here. This is what is EH here. So, we cannot have the same thing on both sides. Okay. So, this when you are writing in terms of EH, we do not mention another activity of electron as we did in PE equations. When we were writing in terms of PE, that is activity of electron, then only we are going to write log K, and in those reactions we were going to write the activity of the electron term, so that we can convert it into PE. But when we are writing EH, when we are writing in terms of EH, we are not going to write the activity of electron term. Now, let us see the natural distribution. Generally, we are going to see these plots of pH and EH. Okay. So, pH axis increasing, and these are the EH values that we often see in the different situations. For example, let us see that the environments which are in contact with the atmosphere. Okay. Environments in contact with the atmosphere, we have mine waters. So, basically on the surface of the earth it is there. So, mine waters, rains, streams, normal ocean water and aerated saline residues. Okay. Let us see the very common rains and streams. So, they are on the surface of the earth. Their pH is mostly circumneutral. So, streams will be between 6 to 7.5, 8. Rain will be slightly acidic 5 to 6. So, they are here and their EH values will be around this much. Okay. Mine waters, they can move into slightly more oxygenated due to the interactions that is happening. They are slightly oxidized, but they are very acidic. Okay. So, they fall in the upper leftmost corner. Then comes our ocean water. Okay. So, ocean water falls within this range 7.8 to 8.34, that kind of pH, and in terms of oxygen it will come here. So, 0.3 to 0.5 EH in volt terms. Saline residues. So, those waters which got separated out from the coastal areas and maybe now in brackish water, you can see brackish systems, slightly low oxygen EH value, but more in terms of alkaline values, they are alkaline little. Transitional environments. Okay. So, here you are moving from the atmosphere direct contact to lower atmospheric contact. Okay. So, bog waters means swamps, bogs, wetlands, those kind of water which is extremely high in the which may not exchange as much oxygen as it is supposed to, and it is not because of the oxygen that is exchange, it is mostly due to the high organic matter that is getting decayed, which is quickly utilizing whatever oxygen is available. So, bog waters and then groundwater. So, bog waters are slightly acidic because of the decaying, there will be lot of humic acid, fulvic, so organic acid rich, which will shift it towards slightly acidic as compared to groundwater. Groundwater, due to its separation from the surface, it will be less in oxygen, okay, less in oxygen content, but it will be more alkaline. Okay. So, it will be between 8 to 9 or sometimes even maybe 10. And those environments which are absolutely isolated from the atmosphere. So, organic saline, eugenic marine, waterlogged soils. So, it is no more exchanging any oxygen for the atmosphere. They are trapped, they are basically trapped water. Okay. So, in marine system, okay, or in some kind of lakes which now have turned very saline and there is a lot of organic matter decaying. So, those kind of water. So, it is moving towards salinity, higher salinity. So, it is extremely alkaline, okay, and of course, it is very reducing due to the decaying of the organic matter. Eugenic marine, okay, again it is trapped in the marine system. So, it is not able to exchange any oxygen, it is trapped, slightly more since it is marine already, it will just shift from here. So, it will start from 8. So, it is moving towards more acidic, maybe 7.5 moving towards just the borderline neutral conditions. And waterlogged soils. Waterlogged soils can be extremely variable, depends on the soil type, organic matter concentration, how long it is residing in that environment. So, all of those factors. So, this is the upper stability limit of water, this is the lower limit of water stability. Beyond this, water is not stable. Okay. So, these are the kind of environments and approximate environments, often generalized environments in terms of EH and pH. And this is called the stability diagrams. Sometimes it is also called the Purbeck diagrams. Okay. Now, how do we draw, how do we create this EH-pH diagrams? Extremely important when we are trying to model certain contaminated systems, and specifically when you are doing mining sector, when you are trying for reclamation, when you are trying to reduce the environmental impact, understanding in which oxidation state it is, what is the different minerals, because now you have a more different system where only certain interactions are happening. It is not as open as in the ocean or as dynamic as in the rivers. Okay. So, different environments we are going to apply different processes, and in specifically contaminated mine water reclamation or landfill, leachate, so or sewage, those kind of effluences entering, and we are trying to address very specific situations, then we need this kind of understanding wherever there is a organic matter interaction and all. Okay. So, here from this particular slide, we are trying to understand how to create the EH-pH diagrams. Okay. We are going to derive these equations here, we are going to find out the slope of the lines, which field will be stable here, what will be stable in this field, what will be stable in this field. Okay. So, let us determine how to find the stability limits of water. Okay. So, H2O, if it is unstable, it is going to form 2H plus half oxygen gas plus 2 electrons it will give out. Using the Nernst equation, we are going to write EH is equal to E0 minus 0.0592 divided by N into log of 1 by this one O2 and H plus. We are not going to write this term, right, we are going to write an EH term. So, no electron in activity of electron term here. Okay. So, whatever is, if it is in gas, we are going to write in terms of pressure of it. Okay. So, pressure of the oxygen and activity of H plus term. Then from this we are going to put in these values. Okay. So, whatever is the pH of the solution, we are going to write. Okay, say suppose you are writing 14. Okay, so you fit in that term, pH term, and you write okay whatever oxygen, atmospheric oxygen, if it is, then it is 1 atmospheric pressure. So, using this we find out the curve. Okay. So, this is the stability limit of water. Okay. So, this is that line. Okay. This is the stability limit. Now, let us draw the let us draw the upper limit of this water. Okay, and that is H2O, that is forming 2H plus half of oxygen gas plus 2 electrons. So, this is okay, this is that equation. Okay. So, here if we know what is E0, okay, if we know what is E0, how do we calculate that? We calculate from the del G0 value, and you know that value, okay, you are going to be provided with that value, or you are going to find out from that further this del G0 R calculation from products minus reactants, okay, and using the number of electrons exchanged. So, here it is 2. So, 2 into the Faraday constant. So, you find out that is 1.23 volts. Okay. So, you plug in this value 1.23. So, minus 0.592 divided by 2 is 0.296. So, now let us separate out the PO2 term and the H2 term. Okay. H plus term and PO2 term, let us separate out. Okay. So, we are going to write in terms now of pressure of oxygen and in terms of pH. Okay. So, given the pH value and the pressure of oxygen, this is my upper stability limit of water. Okay. Now, if you are considering the 1 atmospheric pressure, then this term, okay, log term gets 0, and you are left with only 1.23 minus 0.592 pH. That means it has a constant value, and this is the slope of the line. Okay. So, this is my x and this is my slope, alright. So, this is my curve. Okay. So, this is my 0.0592 curve. So, again if we go back, if I just repeat what we did, we wrote first the equation, then we write the Nernst equation, that is in terms of EH. We always have to find out what is the E0 value. That E0 value, if we have to find out, you can either have to calculate the delta G0 R, the reaction, this free energy of the reaction. So, if that is not provided, you calculate that and find out what is the E0 value, plug in that. Okay. We did that, and then we are going to break down this two such that we have our pH as one term, because we are plotting EH and pH. So, this is my x. So, this is my x term, and this entirely is my intercept. Okay. Now, I will make an assumption and I will say we assume that my PO2 is 1 atmospheric pressure. Okay. So, then this becomes very simple, it just turns to 1.23 minus 0.0592 pH. That leads to a slope of, okay, 0.0592 and intercept of 1.23. Okay. Now, let us see the lower limit. So, hydrogen that is released is going to accept an electron and it is going to form hydrogen gas. Again we are going to write the Nernst equation. So, EH equal to E0 plus 0.0592 divided by 1, because only one electron is getting exchanged, okay, log of pH2 and divided by H plus. Here again we are going to set this at 1 atmosphere. Okay. Also we find that the delta G0 R is 0. So, this E0 terms entirely becomes 0, right. If the delta G0, if the delta GR 0 terms is 0, the E0 term becomes 0. So, then I am only left with this term, that is minus 0.0592 of pH. So, again a similar slope, but it will now start from 0, there is no intercept here, it will just follow the same slope. Let us see another more complicated system. Let us see the FeO2H2O system. Now, in that FeO2H2O system, we will have multiple species, right. We will have Fe2 plus, we will have Fe3 plus, we will have water, we are going to have this FeOH2 and FeOH3. Okay. And we have to find out where it is stable, how it is getting stable. Okay. So, first let us take two species and find out the boundary. Okay. What does the boundary mean? So, here this is the boundary. So, above this my oxygen is stable, below this my water is stable. Again here my water is stable, below this more reducing conditions my hydrogen is stable. So, you should be able to say which species is stable in which particular area in this EHPH plot. So, this is what we call boundaries. Okay. So, first thing that we always do is first we have to write the equation using those two terms wherever the boundary is, with those two terms. So, my FeOH3 ferric hydroxide accepts an electron and a hydrogen to form ferrous hydroxide plus water. Here you see both are pure phases, one is a solid and a liquid. So, we are not going to write that in the K equation. Okay. So, if we are trying to express the K, so we write K is equal to 1 by A to the power E and A to the power H plus only this. All the pure phases, solids and liquids, they are going to be removed. Okay. Now, let us take log. So, log K is equal to minus log of 8 e to the power minus. So, just rewriting this in terms of log terms, and of course, you know that this is equal to Pe and this is equal to pH. So, my log K is equal to Pe plus pH, or in terms of Pe if I write, because I am going to draw a stability diagram. So, it always has to be in terms of pH or either EH or Pe. So, here it will be either in terms of EH or it will be in terms of Pe. So, this is my y, this is my x. Okay. So, Pe is equal to log K minus pH. Now, let us calculate what is log K. To calculate log K, we need to calculate the delta G0 R, right. So, how do we calculate that? From the formation values. So, we are being provided with these values. We are being provided with these values, we just plug in those values. So, it is delta G0 F of FeOH2, delta GF0 of H2O, delta GF0 of FeOH3, and we find out this is the delta G0 R. Now, we know the log K, that is delta G0 R divided by 2.303 RT. So, we from here delta G0 R we calculate what is my log K value, and this comes to 4.75. So, just substitute that value. So, my Pe is equal to 4.75 minus pH, which is a line with a slope of -1 and intercept of 4.75, right. So, again y x, this is -1 is my slope, this is the intercept C. Okay. In terms of y is equal to mx plus C, okay. This is my mx, m is equal to -1 and intercept C is equal to 4.75. Now, let us see how we draw it. So, if you have pH and if we have Pe in this axis, then our intercept is 4.75. So, from 4.75 we draw a line, and what is the slope? The slope is -1. Okay. So, this is our boundary of FeOH2 and FeOH3. Okay. FeOH3 is here, FeOH2 is here. Just forgive this, it just shifted somehow. Next, let us see another boundary. Let us see the FeOH2 and Fe2 plus boundary. We are going to draw many such boundaries, okay, with the species. So, again first we write the balanced reaction FeOH2S, which is in the solid form, plus H plus will give Fe2 plus 2H2. Next thing that we do is we write the K value. So, we write in terms of K. K is equal to A Fe2 plus divided by A H plus whole square. Log K is equal to minus log of A Fe2 plus 2 pH. So, my pH is equal to half of log K minus half of log A of Fe2 plus. So, here you start noticing that Pe is not there. The entire Pe term is only not there. Okay. Let us again go on for solving this. You solve the delta G0 R from the values that has been provided. You calculate the log K value, that comes to 13.61. Fit in that value in that previous this equation. Okay. So, pH now comes to 6.81 minus half of log activity of Fe2 plus. Activity of Fe2 plus is the activity of Fe2 plus in the solution. That means, we have to now find out a concentration. Let us say that is 10 to the power minus 6 moles per liter. If we know this concentration value, we are just going to plug in that value and we get that pH is equal to 9.81, that is our boundary line. Okay. So, pH equal to 9.81, that is our boundary line, this one, okay, for that FeOH2 and Fe2 plus boundary. So, we draw a line randomly, okay, from using this pH equal to 9.81, okay, and this is going to truncate somewhere. Okay, this is going to truncate somewhere. So, for the moment we are going to leave it like this. Next, let us see another boundary, that is FeOH3 and FeOH2 plus boundary. Again, first thing we are going to write the balanced equation. Then we are going to write the K value, write in terms of equilibrium constant. Again, from equilibrium constant take log, write it in terms of Pe and pH. Here we have to find out what is the log K. So, we find out what is the log K, and that is 18.36. Plug in this value in the Pe equation. Again, here we are going to utilize the concentration of iron. So, that was 10 to the power minus 6 mole per liter. So, this gives the final equation as Pe is equal to 24.36 minus 3 pH. So, this is my intercept and minus 3 is my slope. So, now if I have, so 24.36 is my intercept and now I have a minus 3 as the slope. So, I draw a line and I say okay, this is my Fe2 plus and FeOH3 boundary. So, Fe2 plus FeOH3 and this is my FeOH2. Right. So, my 2 two boundaries are present, one I did here, one I did here. Let us see another Fe3 plus and Fe2 plus boundary. Okay. Again we write first the balanced equation, we write what is the equilibrium constant. Okay. Here the Fe2 plus and the Fe3 plus value is equal to 1, okay. The activity is coming down to 1, and so the PE is just dependent on the log K value. So, you find out what is the delta GR, that is equal to the log K, so 12.84, and therefore, my PE is equal to 12.84. So, again this is independent of the pH. So, you draw a line, okay. So, PE is equal to 12.84. Here it truncates again this line. So, you remove this line and you say okay, this is now my Fe3 plus Fe2 plus boundary. Okay. So, above this my Fe2 plus will always move towards the Fe3 plus state. Okay. So, it is a pH independent boundary. Below this PE it is Fe2 plus, above this PE value it is Fe3 plus. Another boundary is required, right. Another boundary between Fe3 plus and FeOH3 plus is required. So, again let us first write the balanced reaction. Okay. Let us first write the balanced reaction. We go ahead and calculate what is the equilibrium constant. So, that comes to pH, okay, this equation. Here we need the log K value. So, we find out what is the delta GR0. From that we find out what is the log K value, which comes to 5.52. We plug in that value and we also plug in the activity of Fe3 plus, that comes to 10 to the power minus 6. Okay. Activity of Fe3 plus is equal to 10 to the power minus 6 mole per liter, already given, and therefore, the pH is equal to 3.84. So, there is no PE term. Okay. So, there this is my pH equal to 384. So, this is my line. Okay. So, this is my final diagram for Fe, H2O and O2 system. So, we see how in what conditions my Fe3 plus is stable, my Fe2 plus is stable, my FeOH3 plus is stable and FeOH2 plus is stable, right. And we see that in most natural waters pH values are in the 5.2 to 8.5 level. So, that means between this to this I will find either iron in the form of iron FeOH3, and if it is going below, if it is going below a certain pH, you may find Fe2 plus. Okay. And it is more soluble. So, more soluble Fe2 plus is in the reducing conditions. Okay. So, with this I end this lecture today, and we are going to see some of the more examples of redox in our next lecture, and I am going to start another new topic in our next lecture. Thank you.